So today we're going to be going over the Euler phi function. So we're going to start off with what is Euler's phi function. So the function written as this symbol, which is our phi symbol, of n counts how many numbers less than n are relatively prime to n, which we can show as phi of n is all the numbers from k in 1 up until n minus 1, such that the GCD of k and our value of n are equal to 1, which is just a fancy way of saying how many numbers from 1 to n minus 1 share no common factors with n except for 1. So our first example is phi of 5. So the numbers less than 5 are 1, 2, 3, and 4. But since 5 we already know is a prime number, we know that all of these numbers are relatively prime to 5, meaning that phi of 5 is equal to 4. And we can show this as the GCD of 1 and 5 is 1, the GCD of 2 and 5 is 1, the GCD of 3 and 5 is 1, and finally the GCD of 4 and 5 is 1, which gives us all our 4 options to give us the answer for 4. Now we have example number 2, which is phi of 8. So the numbers less than 8 are 1, 2, 3, 4, 5, 6, and 7. But which one of these are relatively prime to 8? So we can see that 8 could be broken down into 4 times 2, meaning that any number here that's a multiple of 2, because 4 is just 2 squared, so this is just 2 squared times 2, which is just 2 cubed. So anything that's a multiple of 2, we know isn't going to be relatively prime to 8, meaning our 2, 4, and 6 are gone, which you can check by saying the GCD of 2 and 8 is obviously not going to be equal to 1, so we know that it's out. But this leaves 1, 3, 5, and 7, which we can check. So the GCD of 1 and 8, the GCD of 3 and 8 is 1, the GCD of 5 and 8, we already know that 5 is prime, so anything with a prime is 1, and the same thing for 7. We already know that 7 is a prime number, so anything with 7 is 1, meaning that the set of numbers here is going to be 1, 3, 5, and 7, which means that our phi of 8 is also going to be equal to 4. So now we have Euler's theorem, which, if we know what phi of n is, we can state Euler's theorem, which is if a and n are relatively prime, then a to the power of phi of n is congruent to 1 modulo n, which is a powerful generalization of Fermat's little theorem, which works when n is prime. And then Euler's version works for any positive integer n. So we're going to do this with n of 8. So we already know from our previous questions that phi of 8 is equal to 4. So Euler's theorem states that a to the power of 4 is congruent to 1 modulo 8. And we saw from our previous question which numbers are relatively prime to 8, which was our 1, 3, 5, and 7. So we can start off by checking a being equal to 3 to see what we get. So 3 to the power of 4 gives us 81. And if you do 81 modulo 8, this does give us that it's congruent to 1, which means that it works perfectly. And now let's check for a being equal to 5. So for a equaling to 5, 5 to the power of 4 is equal to 625. And 625 modulo 8 gives us another congruency equal to 1. And then finally, let's check a being equal to 7. So 7 to the power of 4 gives us 2,401. Now let's check this mod 8. Well, 2,401 mod 8 also gives us congruent to 1, meaning that the theorem holds for this question. So now let's talk about the Euler group for multiplicative group mod n. So for n being equal to 8, the group is 1, 3, 5, and 7, since it's all the numbers co-prime to 8. And these are the exact numbers that are invertible modulo 8. And we can say that this group has order 4 because phi of 8 is equal to 4. Order 4. So using this knowledge, we're able to build a table modulo 8. So we have our chart here of modulo 8. So we have 1 and 1 gives us 1, 1 and 3 is 3, 1 and 5 is 5, and 1 and 7 is 7. So now this is multiplicative. So the whole thing is multiplying the numbers together. So this is going to be the same going down because it's all multiplied with 1. But now here's our first difference. 3 and 3, instead of giving us 9, because it's modulo 8, will be giving us 1. And then 3 and 5 gives us 15, which is 7 modulo 8. And 7 and 3 gives us 5 modulo 8. And if you notice, you can see that each row and column contains each element exactly once. So once we get our second number, which is our 5 and 3, which we already know is 7, we can see that these last two options either have to be 1 or 3. But 5 and 5 gives us 1, and finally 7 and 5 gives us 3. Now we can just use what we have from our previous answers to fill in this last section, because we can see it goes 7, 5, 3, so 7, 5, 3, and then finally 1. So not only does every row and column only have each element exactly once, Euler's theorem tells us that raising element of this group to the 4th power gives 1 modulo 8. So now we have more examples, where our first one is n being equal to 10. So the numbers less than 10 are numbers 1 through 9. But 10 can be broken up into 5 times 2, meaning that any number that's a multiple of 5 or 2 cannot be relatively prime to 10, meaning that the numbers relatively prime to 10 are going to become 1, 3, 7, and 9. Since we can see that 2, 4, 5, 6, and 8 are all multiples of either 5 or 2. Now this means that phi of 10 is equal to 4. And if we want to check it to make sure that we're right, we can have our formula of a to the power of our phi of 10, which is 4, being congruent to 1 mod 10. So we can test this for our values of a. So our first one that we could say is a equaling to 3. So this gives us 3 to the power of 4, which is 81, which is congruent to 1 mod 10. So that works. And now let's try it for a equaling to 7. So this is 7 to the power of 4, which is 2,401, which is also congruent to 1 mod 10. So we know that this works as well. And now let's try one more question with n being equal to 12. So 12 is a little different because to break this up, this goes 6 times 2, but 6 can be broken up into 3 times 2. So this whole thing becomes 3 times 2 squared. So any multiple of 3 or 2 we have to say is not relatively prime to 12, meaning that the numbers that are relatively prime are going to be 1, not 2, not 3, but 5, not 6, but 7, not 8, not 9, 10, but 11, meaning that phi of 12 is being equal to 4. So again, our formula is going to be a to the 4 is congruent to 1 modulo 12. And if we want to test this one, we could just use 5 to the power of 4, which is 625, which is congruent to 1 modulo 12. Let me know in the comments which number theory topic you want to see next. Thank you for watching, and I'll see you in the next one.